Alright, in this video we'll be talking about transformers in an NCEA Level 3 context. Okay, so ultimately, a transformer is going to be used to transform either voltage or current, okay? And so what I mean by that is we're going to have an input voltage, if you will, okay, of V, and we're either going to make this voltage higher or we're going to make this voltage lower. Same thing for the current, we're going to have an input current, okay? And we're either going to make this current higher or we're going to make this current lower, okay? And so that's what I mean by we're going to transform the current and the voltage. Okay, so a common example of this is, let's say we have our 240 volt power outlet, and let's say we want to charge our phone, for example. We would want to step down that voltage to a lower value, let's say 10 volts instead, okay? Because that 240 volts is way too high, okay? So first we're going to go through 4 pieces of theory about how electromagnetism works, okay? So the first bit is about inducing an EMF, and the way we can do that, obviously we have a bar magnet right here, and we can pull that bar magnet in and out of the coil, okay? And as we know, this bar magnet is going to have flux lines, right? And as these flux lines interfere with our coil, there is going to be an induced EMF, an induced voltage, and therefore an induced current, okay? And that is obviously due to Faraday's law, like so, okay? And we also know that as we continuously pull the bar magnet in and out, the induced EMF and therefore the induced current is going to flip directions constantly, right? And so our second idea is that if we take this coil and we hook it up to a DC power supply, right? And we obviously know when we do this from level 2 that we get an electromagnet. And so what we're going to have is magnetic field lines coming in through this coil, like so, okay? And so our third point is building on our second point. If we were to replace this DC supply right here with an AC supply, okay? So DC meaning direct current and AC meaning alternating current. And so what that means is the current is going to continuously change directions. And so if we say we have a 60 hertz alternating current, that means that the current is going to change directions 60 times in a second. And because we know that the polarity of our electromagnet, okay, so in this case our north pole's here and our south pole here, okay, so we know that the polarity of our electromagnet is determined by the direction of our current, okay? And so if our current is continuously changing directions, then the polarity of our electromagnet is also going to continuously flip back and forth, okay? And so this fourth point is a combination of 3 and 1, okay? So a combination of this and this right here. As you can see over here, we have 2 coils. One is an AC coil that we had in part 3, okay? And one is just a regular coil that we had in this part right here. If we take a look at what's going on, we have our AC coil, and as I just stated previously, this AC coil is going to have a changing current, okay? So the current is going to be changing, and so therefore the polarity of this electromagnet is going to be continuously changing also. And so therefore, the flux lines from this electromagnet is going to interfere with this coil over here. We are therefore going to have an induced current in this coil right here, okay? And notice the similarities between this and our first point. In this, we had a bar magnet which also has flux lines, and it's interfering with this coil, thus producing an electromagnet in this case, okay? And in this case, we're pulling the magnet in and out. However, in this case, we're doing a very, very similar thing. In this case, we're changing the polarity from north to south to north to south to north to south, okay? On this side specifically, and then the opposite will happen on this side. And therefore, because the polarity is changing over here, when these flux lines interfere with this coil, this is also going to cause the electromagnet in this coil to change polarity also, just like in our first scenario. As we continuously pull the bar magnet in and out, the polarity of this coil is going to alternate also. So you can see how we've combined all of the knowledge that we have into this fourth point to produce this scenario right here, okay? So therefore, we can say that the alternating current results in a constantly changing magnetic field, and therefore this induces a voltage in the second coil that is also constantly changing. And when I mean changing direction, okay? So how do we turn this scenario into a transformer? Well, what we don't do is we don't line them up perfectly like so, okay? So that would be kind of hard to do. So what we do instead is we use an iron core, okay? So the iron core usually isn't this big, okay? It's usually a lot smaller. And what we do is we sort of flip our coils to the side, okay? And then we wrap them around these sides right here, okay? So I'll show you what I mean. So we will have our first coil right here, and this is going to be our AC supply. It goes over here. It's going to wrap around like so, and then wrap around again like so, and then come out like this, okay? And then our second coil is going to wrap around like this, okay? Notice the difference in the number of turns between each coil. That is going to be very important later on. As you can see, this coil has 3 turns and this one has 4 turns, okay? So it's very important that the 2 coils have a different number of turns, and I will show you why that's important later. As for this iron core, the main point of this iron core is to transfer the magnetic flux, okay? So the process of how this happens, I have written over here. We can see that the primary coil, which is using an AC current, produces a constantly changing flux, okay? And so that's what we established up here and over here, okay? Then the iron core transfers this flux to the second coil, okay? So this iron core transfers this flux into this coil right here. And then the changing flux in the secondary coil induces an EMF in the secondary coil due to Faraday's law, okay? And if you don't know what Faraday's law is, I have gone through it in a previous video, so you can go check that out. But essentially it says that whenever we have a changing flux, which is what we do have due to this alternating current, we will have an induced EMF being produced, okay? And the number of coils in the secondary coil determines the size of this EMF, right? And that is our N value right here, okay? So the equation that we use to change our voltage is based on the coil ratios, okay? So that's why I established that the reason why the coils must have a different amount of turns is because it's the ratio of turns that determines our values of our voltages, okay? So as we can see in this equation, the voltage of our primary coil, so the voltage across our primary coil, all over the voltage of our secondary coil is equal to the number of turns of our primary coil all over the number of turns of our secondary coil, okay? And as you can see, this is a ratio, and so let's say we have 1,000 volts coming in, okay, and we want to step it down to, let's say, 10 volts, okay? We can use 1,000 turns over here and then 10 turns over here, okay? So as we can see, this is the exact same ratio, and so the equation will check out. Or what we can do is do 101. So 100 turns and then 1 turn. So although the numbers are different, the ratio between 1,000 and 10 is the same ratio between 100 and 1, okay? And so the equation still checks out. So it's about the ratio of the coils, not necessarily the number itself, okay? So now that we know that, we can apply that to a question. A transformer with 200 coils in the primary has 240 volts across it. How many coils are needed to step down the voltage to 10 volts in the secondary coil, okay? So now figuring out our numbers, we can see that our primary coil has 200 turns, so our NP is equal to 200, okay? So that's the number of turns in our primary coil. And our VP, which is the voltage of our primary, is equal to 240 volts, okay? What we're trying to find is our NS, which is the number of turns in our secondary coil, and we know the value of our VS is equal to 10 volts. And so therefore, because VP all over VS, where P is for primary and S is for secondary, is equal to NP all over NS, plugging in our numbers, we get 240 all over 10 is equal to 200 all over NS, which is what we're trying to find. Now we can rearrange for NS, and we get 200 all over 240 divided by 10, and this gives a value of NS as 8.33 turns, okay? There we go. So this question asked us to step down the voltage, but it seems like I can also step up the voltage, alright? And you'll be right, you can step up the voltage. In this case, we had 200 turns in our primary, so that's heaps of turns right here, okay? So that's going to be way more than that. And we had 8 turns in our secondary. However, if we flip that, if instead we had 8 turns in our primary and 200 turns in our secondary, it seems because of this equation right here, we would actually be able to increase our voltage rather than decrease our voltage. And so you might be thinking, well, that's amazing. We can just get a bunch of voltage for free. This is free energy, right? And in reality, you're partly correct. You can step up your voltage a ton, and that actually happens in power lines, okay? In power lines, they carry immense voltage to keep the current as low as possible, so we limit energy loss, okay? However, this isn't a bunch of free energy, okay? The reason for that is because in an ideal transformer where there is no energy loss, the total power in the primary is equal to the total power in the secondary. And so what actually determines the energy is the P is equal to IV equation, okay? So power is the actual conserved quantity in this case, And because power is the product of both current and voltage, if we step up our voltage, we therefore need to step down our current, okay? So if the voltage increases in our secondary coil compared to our primary coil, the current in our secondary coil is going to be lower than our primary coil, okay? And so that goes back to what I said previously. When we transfer electricity and power lines, we step up the voltage, and therefore as a consequence, the current is stepped down. However, we actually want that because P is equal to I squared R, and therefore if our current is reduced, therefore we're going to have less heat being produced as our power value is also lower, and so therefore we're going to have less energy loss, okay? And so therefore we get a second equation here, which is just the inverse, okay? And so in this case, the current in the secondary all over the current in the primary is equal to the number of turns in the primary all over the number of turns in the secondary. Notice how in the current situation, our primary and secondary are flipped compared to our voltage, okay? And so that reinforces the idea that when we increase our voltage, our power must decrease, okay? And so with this knowledge right here, we can try another question. So a transformer has 540 turns in the primary coil and also has 5 amps in the primary coil. If the secondary coil has 1 turn, what is the current in the secondary coil? So we obviously know our equation, IS all over IP is equal to VP all over VS, okay? We're trying to find the current in the secondary coil, and so we can rearrange for that, and we get VP all over VS multiplied by IP, okay? We know the current in our primary coil is 5 amps. We have 540 turns in our primary and 1 turn in our secondary, okay? And so therefore, IS is equal to 540 all over 1 multiplied by 5, and this gives a current in the secondary as 2,700 amps. And this is a wildly huge current value, okay? And remember, when we have these ridiculously large current values, this is when we're going to have a bunch of heat being produced, okay? And so that will be it for transformers. See ya.